Hey everyone. So in this video I like to talk about solving trigonometric equations. So I'd like to begin by saying that when we solve an equation, we're really looking for all of the solutions to that equation. For example, if I wanted to solve the quadratic equation, x squared plus 5x plus 6 is equal to 0, well, I can imagine factoring this left side to get x plus 2 times x plus 3 is equal to 0, and we get the two solutions. Right, one corresponding to when each factor is equal to 0. We get the two solutions, x is equal to -2 and x is equal to -3, right? So when we're trying to solve this equation, we're really looking for both of these solutions. And so typically, and even in the case when we're trying to solve trigonometric equations, we want to find all of the solutions to that equation. Right, so let's say I wanted to solve sine of theta is equal to 1/2. And so what we want to do is we want to determine all the values of theta, find all angles theta such that sine of theta gives us 1/2 out at the end of the day. And we know that sine of theta, it gives us the y coordinate of that angle, or on the point on the unit circle corresponding to that angle of theta. And so if we look at the unit circle, then sine of theta is going to give us 1/2. Well, here's the y value of 1/2. And we get these 2 points out here that have a y coordinate on the unit circle of 1/2. So any angle that brings us to these 2 points here would be solutions to the equation. So, one such angle might be here, and one such angle might be out here. And of course, we can go around the unit circle many more times and end up at the same points here. So actually there's infinitely many solutions to this equation, right? But we get one solution for the family of angles that fall on this, or coterminal to this position here. And we get another family of solutions that correspond to any angles that are coterminal to this one here. So one set of solutions, well, I can sort of picture pi over 6 working, right? Sine of pi over 6 gives us 1/2. And if I added on another 2 pi to this, I would get 13 pi over 6. And this would also work, right? 13 pi over 6 corresponds to a coterminal angle to pi over 6 and would give us the same sine value of 1/2. Similarly, if I added on another 2 pi, and I got, well, then 2 pi is the same as 12 pi over 6. So if I added on another 12 pi over 6, I would get 25 pi over 6. And so on and so on and so on. There'd be infinitely many solutions corresponding to all angles coterminal with that purple angle here. And really, I could write this more concisely as pi over 6, right? One example of a solution added on with multiples of 2 pi. So 2 pi times n, where here n is some integer. Right, so here is an infinite set of solutions to this equation here, but that's not all of the solutions, right? We get another family of solutions corresponding to any angle that falls on that blue line. And so one such angle that does the job, that falls on that blue line, is 5 pi over 6. Right, when we have an angle of 5 pi over 6, we're leaving that 30-degree angle to the x-axis. There's a 30, 60, 90 triangle that fits in there with a side length of 1/2 here, giving us a y coordinate of 1/2. Right, so 5 pi over 6, an angle of 5 pi over 6 is one solution to this equation, but again, we get another solution for every coterminal angle. Right, so I can imagine adding on another 2 pi, giving me, that would be 17 pi over 6. I can imagine subtracting off another 2 pi, giving me, well, that would be, what is that, -7 pi over 6. And there would be, again, infinitely many solutions, but we can write this more concisely as theta is equal to we could just take one example of a solution that falls on such an angle, falls at such a position, and add on any multiples of 2 pi to get all the other coterminal angles. Again, where that n is an integer. So really the solutions to this equation, well, they're all of these angles here, and they're all of these angles here, right? And none of them overlap. And so here, these are the solutions. And so the idea with solving this example of an equation, a trigonometric equation, is that we wanted to find all solutions on one period first of our trigonometric function. Right? When we look at this picture here, we found the solutions, all the solutions on one period from 0 to 2 pi. We found the solution pi over 6, and we found the solution 5 pi over 6. And there aren't any other solutions in this one period. And after that, we want to include all the other coterminal angles to get all the other solutions. So here we want to find all solutions on one period. Then include all the coterminal angles. So let's go ahead and take a look at this other example where we want to solve the equation tangent of theta is equal to -1. I definitely encourage you to pause the video and try this example out yourself first, and then we can go over it together. So there are two things I want you to keep in mind when you're solving this equation. One is that tangent takes in some angle and gives us the slope of that angle. So I can view this slope here, or this -1, as the slope of any solution angle theta. And the other thing we want to keep in mind is that, well, tangent has a period not of 2 pi, but of just pi. Right? If tangent gives us the slope of an angle, well, an angle that's all the way on the other side of that unit circle, in other words, pi tacked onto such an angle, it would have the same slope. Right? It would correspond to the other side of the same line. So tangent has a period of pi, and so here really what we want to do is we want to find one such angle with the slope of -1/2, not 1/2, -1. And so that's the line with the slope of -1, and here we can see that one such angle, at least on the period from 0 to pi. Well, that would be 3 pi over 4. And if I added on pi, I would end up with another angle that gives us a tangent of -1, right here at 7 pi over 4. If I tacked on another pi, I would end up at 11 pi over 4. And we would get, again, another angle which has a slope of -1. And so here, what we're really looking at is that theta, well, one example of a solution to this equation is 3 pi over 4. But because the period of tangent is just pi, really we get other solutions when we add on multiples of pi to this angle here. And then there aren't any other solutions to this equation. So I have another example here I want to take a look at. It's a little bit messier than the previous examples, but it's not too different. So, our previous examples, we had that trigonometric function completely alone on one side of the equation, and that helped us solve the equation. And so here, I want to do the same thing. I want to get this cosine of theta alone on one side of the equation. And I can do this by subtracting 3 square root 3 from both sides of this equation. And so I want to figure out, well, the square root of 3 minus 3 square root 3. Right, what is this equal to? Well, it's -2 sets of the square root of 3. It's very similar to if I had, x take away 3x. They're like terms, and so we have -2 sets of x. And so here we are left with the equation 4 times cosine of theta is equal to -2 square root of 3. And so to get cosine of theta alone, we can divide both sides by 4, and we get cosine of theta is equal to negative square root of 3 over 2. And so cosine of theta, what does it do? It gives us the x-coordinate corresponding to an angle of theta. So we want to look for all the angles which correspond to an x-coordinate of negative square root of 3 over 2 on the unit circle. And so here, if I draw that out, negative square root of 3 over 2 as an x-coordinate looks something like this. Actually, maybe I can do that a little bit better. So negative square root of 3 over 2. Well, any points end up out here with an x-coordinate of negative square root of 3 over 2 would correspond to solutions to this equation. So, one such angle might look like so, and another such angle might look maybe like this. Right, again, there's this 30, 60, 90 triangle that fits into this picture. I can imagine one angle that does the job, that gives me this sort of top angle up here to be 5 pi over 6. Right, cosine of 5 pi over 6, well, there's that 30, 60, 90 triangle, and cosine of 5 pi over 6 would give us that x-coordinate, which is the sort of longer side of this 30, 60, 90 triangle, at least, but also with this negative sign attached. So this is one such angle that does the job. But right, any coterminal angle would also work, and so we would have to add on 2 pi times n. And then here, any angle that falls in this bottom coordinate, reaches this bottom coordinate with an x-coordinate of negative square root of 3 over 2. This would also be a solution to this equation, and it's not captured by this family of solutions we've written in pink. Right? And so, again, we see this 30, 60, 90 triangle in this picture, but it's sort of on the other side of this x-axis. Really, there's, with this 30 degree added onto our 180 degrees. So this is really the same as 7 pi over 6 if we're just looking at the period from 0 to 2 pi. And so one solution to this equation would be 7 pi over 6. And any coterminal angle would also work, so 2 plus 2 pi n added on to 7 pi over 6. And then there aren't any other points on this unit circle which correspond to an x-coordinate of negative square root of 3 over 2, so we found all of the solutions. So another common kind of trigonometric equation that we'll want to be able to solve are ones where the input is scaled. Right, so here I have the example, solve sine of 2 theta is equal to 1/2. And one thing I want to warn you about before we really dig into actually solving this equation is that we can't do much about that 2. Right, so because it's in the input of this function, there's not really a nice way to sort of deal with it. We can't divide it out. We can't factor it. It's sort of trapped inside this function of sine, which isn't the nicest function. So there's not really a great way to get inside. So we just have to sort of take this into account when we're trying to find the solutions to this equation. Right, so maybe I'll just write it out here that we can't divide out or factor out this 2. It would be so much friendlier if we were just dealing with a sine function without this 2 theta, but that's what we've got to work with. And so here, we've already solved the equation sine of theta is equal to 1/2, so we have some idea of what the solutions are to this equation, right? Here's sine of theta. Maybe I'll just write this off to this side. Sine of, if it were just theta, is equal to 1/2. We saw that this was true when theta is equal to pi over 6 and 5 pi over 6. Those were one solution, or these were two solutions in the one period from 0 to 2 pi. And we got other solutions for any coterminal angles to these two angles. Right, these are solutions to just sine of theta is equal to 1/2 without that extra factor of 2 in the input. And these equations, they feel very similar. They should be related. And you can kind of think of it like this, right? Here, I know we have this factor, we have this 2 theta in the input of our sine function, but really whenever 2 theta whenever 2 theta becomes one of these angles here, maybe I'll write it like this. Whenever 2 theta becomes one of these angles, we'd be taking sine of the same amount and we'd get 1/2. Whenever 2 theta is pi over 6 plus 2 pi n, or 5 pi over 6 plus 2 pi n, then we'd be taking sine of that angle, and as we see, sine of that angle would be 1/2. Right, so this is what we achieved earlier, but I want to use that now to say that 2 theta must be pi over 6 plus 2 pi n. Right, if 2 theta comes out to pi over 6 plus 2 pi n, then sine of that will give us 1/2. Or if 2 theta becomes 5 pi over 6 plus 2 pi n, well, sine of that will also give me 1/2. And so, this kind of looks a little bit messy, but we can solve these equations for theta and figure out exactly what angles would work. Right, so here if I divide both sides by 2, then this leads me to theta is equal to, when you take an equation and you divide both sides by 2, you want to make sure you're dividing the entire right side by 2 as well. Right, so here I wanted to take pi over 6 and I would divide that by 2, and 2 pi n and divide that by 2. Well, pi over 6 divided by 2 is pi over 12. And 2 pi n divided by 2, well, that's just plus pi n. And if I take the second set of solutions and I divide both sides of the equation by 2, well, I get another family of solutions. I get, this is theta is equal to 5 pi over 6, not pi over 6, 5 pi over 12, sorry about that, plus pi n. And so these are the solutions to our equation. Sine of 2 theta is equal to 1/2. Really, these are the angles which double to solutions of sine of theta is equal to 1/2. And so here, maybe let's check one example. All right, so here maybe let's look at this family of solutions. One such solution would be if we had pi over 12 plus pi, right? One solution is pi over 12 plus pi times 1, right? And this would be equal to 13 pi over 12. So let's check 13 pi over 12. Let's see that this is in fact a solution to our equation sine of 2 theta is equal to 1/2. Right, so here if we plug in 13 pi over 12 into sine of 2 times theta, so it's sine of 2 times 13 pi over 12. We want to see, we don't know this yet, but we want to see if this is equal to 1/2. Well, sine of 2 times 13 pi over 12, that's the same as sine of, 2 times 13 pi over 12 is the same as 13 pi over 6. And 13 pi over 6, right, really I can see this as, this is 12 pi over 6 plus pi over 6. And we know 12 pi over 6. This is really just 2 pi. Right, so here, if I look at my unit circle, what we're saying here with this 13 pi over 6, that's pi over 6, which corresponds to the point, this is the square root of 3 over 2 comma 1/2. Added on with this 2 pi. Right, this is the angle 13 pi over 6, and sine of 13 pi over 6 would be that y coordinate, 1/2. So sine of 13 pi over 6 does make this equation true. Or sorry, sine of 13 pi over 6 would give us 1/2, so it's telling us that the angle 13 pi over 12 would be a solution to this equation, and really that came from this family here, this first family here. And so really what we did was we said, okay, I know we have an input of 2 theta in this sine function, but we can sort of take a step back and look at the big picture. When is sine going to give us an output of 1/2? And those angles, well, we're looking for when 2 theta gives us those angles, right? So here, that's where we ended up with these equations. When 2 theta gives us the angles such that sine produces 1/2. And we could divide both sides by 2 to get the solutions to our equation sine of 2 theta is equal to 1/2. Okay, so let's do another example where the input is scaled. I know these kinds of problems can be a little bit tricky whenever you're dealing with changing the input of a function, and so let's go ahead and get some practice with that. So let's solve this equation. 2 cosine of 3 theta is equal to the square root of 2. So the first thing we want to do is we want to isolate that trigonometric function. So we want to divide both sides by that factor of 2. So this brings us to the equation cosine of 3 theta is equal to the square root of 2 over 2. And so in our previous example, when we solved sine of 2 theta was equal to 1/2, we first looked at when sine of just theta was equal to 1/2. And then we sort of made the adjustment corresponding to that factor of 2 theta of the input. And so let me first take a look at, let's just look at when cosine of not 3 theta, but just cosine of theta is equal to the square root of 2 over 2. Right, so cosine takes in an angle and it gives us the x-coordinate on the unit circle corresponding to that angle. So if we draw out the unit circle, then what we're really looking for here, and this is going to be relevant to our set of solutions, are the angles which give us an x-coordinate of the square root of 2 over 2. All right, so here we can see, one angle that would bring us to an x-coordinate of the square root of 2 over 2 would be pi over 4. Right, another angle that would do the job and bring us to an x-coordinate of the square root of 2 over 2 would be this angle down here. And of course, there's many angles that do this job, but one such angle would be 7 pi over 4. And so, these are two angles that cosine of these angles give us the square root of 2 over 2. And, any coterminal angles to these two would also give us cosine of that angle would give us the square root of 2 over 2. And so what we're saying here is that, 3 theta should bring us to these angles, so that when we take the cosine of them, we'll get the square root of 2 over 2. Right, so we're saying that 3 theta, well, that should equal pi over 4 plus any of its coterminal angles, 2 pi n. Because if 3 theta is if it brings us to this family of angles, then cosine of that angle will give us the square root of 2 over 2. And then similarly, if 3 theta brings us to this family of angles, then when we take cosine of that result, we'll again get the square root of 2 over 2. So really here, if 3 theta is equal to 7 pi over 4 plus 2 pi n, we also get a solution to our equation. And we don't want 3 theta, we want to figure out exactly the values of theta itself that make this equation true. So here, what we need to do is we need to divide both sides of both of these equations by 3. And so this brings us to, well, theta is equal to, well, pi over 4 divided by 3 is pi over 12, plus 2 pi, and so that's 2 pi over 3 times n. And then if we divide both sides of the second equation by 3, we get theta is equal to, well, that's 7 pi over 12 plus 2 pi over 3 times n. So these are the solutions to our equation.